It's a great pleasure for me to introduce today's speaker for this COMET Plus webinar, Dr. Dario Solano, because I know him since 2015. So Dr. Dario Solano obtained a bachelor in geological engineering in 2013. Then he received a Fulbright scholarship to do his PhD in the US at the University of Miami under the supervisor of Professor Szymon Dowinski. This is actually at that time that we met, as I was a postdoc in Miami at that time. After obtaining his PhD in 2018, Dario did 1 year postdoc at the Florida International University. Then he moved back to his home country in 2019, and since then, he's an associate professor at the Universidad Nacional Autónoma de México. They are lucky to have him because he's a successful young scientist. Currently, he's the PI of SAR, a project aiming to produce national-wide ground deformation mapping over Mexico. And all this year, Dario used INSAR techniques to study especially the large subsidence signal over Mexico City, its potential link with tectonic earthquakes, as well as its implications to the collective transport system. And the latter point is actually the topic of his talk today. Dario, the screen is all yours. You can now start your presentation.
Yeah. Hi, everyone. Thank you so much for having me today to present part of my work. I'm very grateful for the invitation and the opportunity. I want to turn off my camera just because I get a little nervous because I feel like I'm being watched. but I'm gonna be here with you. So what you see here in this first slide is an 88-day X-band interferogram over Mexico City from TSX SAR pair. And what I want you to see here is that you see a lot of colors in the middle part. This middle part is the lake zone and is going to be important throughout the presentation. And I want to thank all my co-authors in this work, Szymon Dowinski, Enrique Cabral-Cano, and Batuhan Osmanoglu, for their help and their collaboration. This is a very extensive work we have been working on for quite a while already and became very relevant recently. So let me go through, okay, there. So as I was telling you, the lake zone is important in this work, but we have actually 3 zones in the city: the lake zone, the transition zone, and the hill zone. This is a zoning that the city uses to decide where to build the city, where to develop taller buildings and all of that. Usually they prefer the hills zone, but as you can see, most of the city is located in the lake zone. So anyways, the transition zone is very relevant because if you have a building located in the middle, right, of the hill zone, and then this is the transition zone and this is the lake zone. In the lake zone, you expect to have thick sediments that over the time tend to subside. But in this case, the building is located partly in a stable area and then partly in a subsiding area. So what you get at the end is this kind of effect on the infrastructure that suffers damage throughout the time. And then that happens everywhere in the city. And in this other example, you can see the metro and the metro running through this transition zone here. And as you can see, this area subsides, and this area is, if not stable, at least is subsiding at a slower rate, right? And that happens really everywhere in the city. We can see many examples of that occurring in this case. For example, you see how the cars have to go through this change in the topography, right, in the level of the street, and then make repairs like pretty often over here. Of course, the railways tend to bend due to such differential subsidence occurring in this transition zone, and trains have to slow down to prevent an accident. And this looks pretty bad, right? But now imagine it rains. In such cases, those uneven railways flood and trains stop working. And that's the day-to-day of the 4.5 million riders of the metro system. In our research, we quantify the differential subsidence affecting the metro system and try to link it to the damage in the infrastructure. And also we find that this differential subsidence is a contributing factor in several recent accidents, at least with the reports that we can collect from the media and the news. The outline of this presentation goes through an introduction, then we have a SAR data processing explanation, then we have our INSAR results, and we explore two tools in this work. One is the subsidence gradient, and the other one is the bandpass filtering. And then we talk about how these results can help to understand the damage to the metro system. And particularly, we present some of the results we obtained from the recent May 3rd, 2021 Olivos viaduct collapse that became very relevant in the news, and you could see everywhere in the newspapers. And then a summary of the work. Mexico is located in a very active tectonic setting, and we have the collision between two plates that generate a lot of earthquakes in the southern part of the city. But this collision also, this plate boundary also generates a volcanic arc that goes from one side of the country to the other, right? And in this part that is called the Mexican volcanic belt, we have Mexico City right in the middle. So pretty much the city is located in the middle of a lake, right, that is formed by all these mountains, volcanic mountains, that produced a lot of sediments and then generated the accumulation of sediment layers up to 500 meters of thickness. And pretty much the way subsidence works is that you have groundwater extraction from wells all over the city, because you need to supply the people over there. And more than 70% of the water supply comes from the underground. So it's a huge volume of water that you need to extract in order to provide people in the city with water. And in this very realistic example that I put over here, I have an elephant in a vase, and we have in this vase several sponges, right, piled up, and then we have water filling the empty spaces in the sponges. So if we have this elephant in the vase and it's just standing there, the sponges probably will stand the weight of the elephant because of all the water that is helping, to distribute the load and to fill the pores of the sponges, and it makes it more stable. But then if you have groundwater extraction, or lots of pumping from this vase, you lower the level of the water in the vase, and then the elephant is still pretty heavy, and the load cannot be held by the sponge anymore because of the lack of water filling the pores. So that's pretty much how it works in Mexico City. If we have a little pumping, then sorry. Sorry. If you have a little pumping, then the groundwater level is okay, and then whatever you have on top of the layers of sediment will be, just stable. But then if you start pumping a lot of water, all the stress generated by the pumping, plus the changes in the stress by the lack of water in the sediment layers, plus the load from the rock itself or sediment layers themselves, and the houses, on top of the city, make the land subside, right? And then what happens to infrastructure? Well, it varies, and it occurs in different scales that we're going to talk about. So the main tool that we use to study the metro system is this technique called interferometric SAR. And with interferometric SAR, we have a couple of SAR images that help us calculate the phase difference between two images, right? Like each of these SAR acquisitions acquire or measure the you know, like they have a pulse that goes to the surface of the Earth from a satellite, and then the satellite records with a sensor the amplitude and the phase of the wave coming back, or at least like a wall of waves coming back to the satellite. And then with two SAR images, you can compute the difference of the phase and generate these maps that we call in the INSAR community rainbow maps or interferograms. And what you get visually from an interferogram is that if you see a lot of bands of color, right, like between point A and point B, this means that you have a lot of displacement in the period of observation between the first and the second acquisition. In this case, in 88 days, you have 1, 2, 3, 4 cycles, at least 4 full cycles. And then you multiply those cycles by half of the wavelength of the radar that you're using. In this case, we use C-band and X-band. And that's pretty much how it works at the interferogram level. But then you can have a bunch of SAR images and produce a bunch of interferograms. And then you can process a lot of data to obtain the velocity of deformation. In this case, we use 3 X-band datasets and 2 C-band datasets. The 3 X-band datasets come from the TSX or TerreX satellite and the Cosmos COMET constellation. For the TerreX dataset, we have 34 scenes. For the Cosmos COMET datasets, we have different geometry acquisitions or different characteristics of the incidence angle for the SAR images. So we had to divide the Cosmos COMET scenes into 2 datasets that we call Cosmo 1 and Cosmo 2. And for the TerreX dataset, we call it just TSX, right? The 2 Cosmo 1 datasets were acquired in a 6-month period, more or less. And the TSX dataset was acquired in a 2-year period, more or less. Then we have 2 C-band datasets. In this case, the C-band data comes from the Sentinel satellites, Sentinel A and B, Sentinel 1A and B satellites. And we have 2 orbits, the ascending orbit and the descending orbit. For each of the orbits, we have 250 and 300 scenes. So that helps us to make a more robust solution for the subsidence process, and also in a longer period of time from 2014 or at the end of 2014 to 2021. And we use these C-band datasets kind of as an aid to characterize the regional subsidence signal in the city. The advantage of the X-band datasets is that they have a higher spatial resolution, so that makes them very convenient for the monitoring of infrastructure, which is the main goal of this work. Also, we use 2 different processing techniques. For the X-band dataset, we use PS-INSAR, and for the C-band datasets, we use an SBAS algorithm. The PS-INSAR has the goal to provide the highest possible resolution with the high resolution datasets, and the SBAS algorithm has the goal to provide a robust solution with all this data. And it's a bunch of data, right? Like Sentinel, each of the Sentinel scenes can be between 2 and 4 gigabytes. So imagine that times 250 or times 300. So it is a lot of data to invert. these are the results we obtained from the 3 X-band datasets from the TSX and the Cosmo 1 and Cosmo 2 datasets. And you can see that the solutions are pretty similar. We project the LOS results into the vertical component. And the two outlines that we have over there are the limits of the lake zone and the hill zone, just to make them more easier to navigate between them, because they don't have the same exactly spatial coverage. And these are the results from the C-band datasets. In this case, each of the Sentinel datasets have a different geometry, of course, and then we can combine them to obtain the vertical component from the two viewing geometries. What we can see is that, for instance, in this TSX solution, if we look at these two little spots over here, we see that they deform, or we capture them as deforming areas. However, in the Sentinel solutions, we see that they are captured as stable areas. These two are important because the metro system runs across them, and across other isolated stable areas in the city. And I want you to notice that the Cosmo 2 solution has these two areas as stable, right? These two areas are called Peñón Viejo and Peñón de los Baños. And we're going to be talking about them also in the rest of this work. And we're very happy that the solutions look pretty similar, because that means that INSAR works. And also, if you want to check a denser study on a lot of SAR data to see the subsiding signal in the city, I invite you to check out this work led by Geohazards and published recently. Anyway, in our work, we want to compare the X-band datasets to the C-band datasets, just to make sure that we have a reliable solution for the subsiding signal. And what we can see from here is that the Cosmo 2 solution, compared to the Sentinel results, produces a very small RMSE, right? So that means that both solutions are pretty similar. And in the rest of the comparisons, we see kind of larger residuals, which means that that the solutions are not very similar among them. The two areas of interest that I mentioned, this Peñón de los Baños and Peñón Viejo, are very important for this study. So we kind of take the mean and the standard deviation of those little areas over there, just to make sure that the solutions compare well among them. And C is the comparison between Sentinel and Cosmo 2 results. So as you can see over here, C shows the smallest average of the residuals, right? For as compared to the other comparisons of the solutions. So what we learn from this residuals comparison is that Cosmo 2 solution is very, very, very similar to the Sentinel results, even though Cosmo 2 results or Cosmo 2 SAR scenes were acquired in a 6-month period, but there are enough scenes to make a very reliable solution that we use for our study. But still, sometimes the question that why is Cosmo 2 solution more reliable than Terre X solution? Sometimes someone asks that question, and then we kind of did this little experiment to see why Cosmo 2 solutions were more reliable, especially in this Peñón. This is Peñón de los Baños. And what we found is that the PS density around Peñón de los Baños is lower for the TSX solution, probably because TSX data spans over a 2-year period, and Cosmo 2 data spans over a 6-month period, so the amplitude is more stable over time. And that has an impact in the unwrapping algorithm. We took profiles from one side of the peñón to the other, just to check how the unwrapping, a very simple 1D unwrapping, turns out. And then we see that the Cosmo 2 results don't have any problem with the unwrapping, but then the TSX interferograms have problems with the unwrapping because the sampling is just not enough to have an unambiguous solution of the unwrapping. So that produces that these two stable areas don't show as stable in the TSX and also in the Cosmo 1 results. But subsidence signal changes a lot, like all over the city. In this case, we have this profile ABC that goes all over the city, and we see that we have a lot of variations in the subsidence signal. Some of them are correlated with the geotechnical properties of the materials in the area, but some others are not as obvious. Still, we have different wavelengths of the subsidence signal occurring all over the city. In this case here, we show the cathedral in the downtown of Mexico City. This cathedral was built on top of 2 layers that civil engineers call the hard layers of the city. These 2 hard layers work as a stable area for piling big buildings. So what that produces is that the buildings subside at a slower rate than the surroundings, producing this effect called apparent uplift. And this is the local subsidence in the surroundings of the building, and this is the apparent uplift. You can see that the delta of the subsidence here is 20 millimeters per year. And that happens all over the city. If we take a closer look in another area over here, right? This red square is this square over here, and then this black line is a metro line. Then if we look at this very little black rectangle over here, we can see that the metro line produces apparent uplift all along the bridge. This is an elevated segment of the metro lines. And you see that the line shows as blue, and that means that it's surrounding like at a slightly slower rate than the surroundings. And then if we take kind of transects across the metro line, we can detect the average uplift of the metro line, of the elevated metro line. And that shows like in the infrastructure as these kind of things, right? When you go to this station, for example, that is Pantitlan, you can see that the floors are all cracked, and you sometimes kind of trip when there is a lot of people and you cannot see the ground. You trip because the conditions of the floors are usually pretty bad, and that has to do also with the foundations of the infrastructure, right? Of the bridges that they use to build the elevated overpasses of the metro. But one of the questions also is if these signals are present all over the city or they're just very localized. So for that, we need to understand the spatial structure of the signal. And for that, we have this tool that is called a semivariogram. How it works is that you evaluate the value of subsidence in one point, and then you evaluate the value of subsidence in another point. And you do that all over the city as a function of the vector connecting these two samples, right? And this is called semivariance, and you obtain this plot called a semivariogram. And what we can see from here is that the behavior of the semivariogram is pretty notorious to be almost cyclic. That has to do with the shape of the signal that resembles a bowl. But then very short distances in the first 800 meters of the semivariogram, you have a tendency to preserve the spatial structure of the signal, which means that there are a lot of signals with very short wavelength that are present all over the city, right? And they're usually masked by the very long wavelength subsidence, the regional subsidence. So the metro systems, the metro lines spread all over the city and over areas with very different geotechnical characteristics, transitioning from the lake zone to the stable hills, going through the transition zones. Such variations in the underground materials produce differential subsidence, and all the points and patches in the map mark locations of malfunctioning of the metro system due to subsidence. The metro system has different construction methods, and thus the impact and consequences of differential subsidence vary. For example, along street level, so these are the different methods of, like that they use to build the metro lines. And along street level railways, you can see that differential subsidence produces railway bending, and in elevated viaducts, you can see this effect of apparent uplift. And this happens like everywhere in the metro system. So from the 3X band high resolution datasets that we have, we prefer the COSMO 2 solution for the reasons that we mentioned before, but also because the coverage of the COSMO 2 dataset is really good in the eastern part of the city that we cannot capture fully with the COSMO 1 and TSX datasets. So we stick to the COSMO 2 results for the evaluation of the metro system, but still compare it to Sentinel results just to make sure that the results make sense. The first tool that we use to analyze the subsidence signal is this one called subsidence gradient. And as we mentioned before, we can see that, for instance, in the railways, after they experience subsidence, they bend, right? And that has to do with the conditions of the underground. But at the end of the day, what changes is the shape of the railways, that affects the performance of the trains, and also changes the slopes of the railways. And that's a big problem because trains are designed to work with certain slopes, and if the brakes don't have these safe slopes, they don't work. So you can have an accident and a crash or something like that, and we'll see that later. And also we can evaluate the differential subsidence between columns with this tool. So we decide to use rectangles of 30 meters by 10 meters because this is a satellite image of Metro Line 12 when it was under construction. So we measured like the distance between several piles along the line, and we found that in average they measured 30 meters, and we assume that the same holds for the whole city. We measured this over some lengths of the metro system, and we find that that's a very useful distance to consider. So we kind of discretize the subsidence velocities along the metro lines in these 30 by 10 meters rectangles, and with that we make a calculation for this SI that we call subsidence gradient, and what we obtain is kind of a smooth estimate of the differential subsidence occurring along the metro lines. Over here in this figure we can see the comparison of the velocities obtained from the different solutions that we produced with INSAR. The black triangles are the results from Sentinel. The green dots are the results from the COSMO 2 solution, and red and blue are TSX and COSMO 1. But it's important to notice that Sentinel and COSMO 2 solutions are pretty similar, like pretty much everywhere along the metro lines, and that's very useful because that helps us to see that COSMO 2 is a reliable solution. But what we see in this smaller plot, like under each of the velocity profiles, is the comparison of the gradient using Sentinel and Cosmo 2 results. With Sentinel results, we see the gradients in gray, and with Cosmo 2 results, we see the gradients in black. So what we see is that they are pretty similar, but in general, results from Sentinel, gradients from Sentinel results are smoother. And if we take all the gradients from all over the city, we can see that in this comparison, right? Like the histogram of the Sentinel solution is just closer to zero, right? Tends to produce gradients closer to zero, and higher density sampling allows a wider range of gradients. The second tool we use is this bandpass filtering from Cosmo 2 results as well. And what we assume is that the signal can be evaluated in terms of the spatial wavelength of the rates, right? So we consider the spatial wavelength or the inverse, which is the spatial frequency. And then for that, we make these little examples just to see what would be the appearance of the frequency, in the frequency space of each one of these signals, and we see that the longer spatial wavelengths are represented like closer to the center power spectrum. So we use that to filter our signal in this method that we created, in which we analyze the power spectrum, and then we try to find a threshold with an algorithmic approach to segment the profiles or some profiles of the power spectrum, and we also analyze the spatial behavior of the signals related to infrastructure in the city. And with those two thresholds, we can filter using bandpass filtering, and we published that in a paper. It's a methodology we developed, but the results look pretty much like this. This is the original signal, and then this is the low spatial frequency signal, the intermediate spatial frequency signal, and the high spatial frequency signal. These are the three components that we obtain. You can see all the details in this other work of ours, but the signal of interest is this intermediate spatial frequency or intermediate wavelength that we call the local signals, right? That are relevant to infrastructure monitoring. And with that intermediate wavelength component, we can see the apparent uplift of several metro lines, and also of some other large buildings that use foundations that go all the way to the hard layers in the underground. And for instance, one of the examples that we saw before is located over here and experiences apparent uplift. And this other example is a pedestrian bridge in a station called Pantitlan, which is composed by several overpasses. And what happens over there is that you have this kind of instability in the bridges that looks really dangerous when you go over there. All right, so the subsidence gradient, which is the first tool that we used for this evaluation along the surface segments, revealed some very interesting details. For instance, over here in this location marked as C, we detected, or we gather from the news that there was an accident in 2015 that was related to this brakes capability of the trains passing by, and that's close to this station called Oceania. So what we learned from this gradient analysis is that the subsidence, the differential subsidence, changed the slope of the terrain and then changed the capacity or diminished the capacity of the brakes to work under such conditions. Over here, this line has a lot of problems. It's called line A, and usually has a lot of problems around Peñón Viejo, and we see that the subsidence gradient is very high in the surroundings of the Peñón, producing very high differential subsidence, and they usually have floods, and they have also service interruptions because they need to re-level the roadways. What was very interesting is that this line built in 2012 had also very high gradients, but didn't have any reports on differential subsidence in the news. And we assume that that's because it's very young. It's a very young line that hasn't developed a lot of problems. But in line A is you get this happening every time that it rains heavily in the city. And I've been there, and it's not funny. It looks like a lot of fun, but it's not. You need to walk a lot to, to go from one station to the other. Just you need to walk all the way here, and that's why the cops are here helping people, to go through these places. Anyways, along elevated segments, we also find very interesting results. The Olivos accident occurred in an area where we have fairly high differential subsidence, as shown by our subsidence gradient results. And what this subsidence, differential subsidence generates in these elevated overpasses is this effect, right? You have the columns, and then you have the bridge connecting the columns, but then if one of the columns moves at a higher velocity than the other, then you lose stability in the connecting bridges. And you can see that in several examples all over the city. Usually they perform maintenance on these structures, so just to keep the operations safe. But then they also have a regulation, an official regulation in the city that they term service limit states. And with those, you can kind of measure or estimate how much deformation you can withstand with the bridges without having any problems. And they say you should have this much deformation in 50 years, right? So the expected time to reach the SLS in the city is not less than 50 years. However, in this area where the Olivos accident occurred, the time to reach the SLS was 11 years. So even though differential subsidence is not explicitly mentioned as a contributing factor in the collapse of the bridges, we find that there is a very high differential subsidence in the area. And this looks as if we prepared the figure just to show exactly the high differential subsidence value, to match the location of the accident. But no, we actually obtained these results a few years back, way before the accident. So also with this analysis of the intermediate wavelength component of the subsidence signal, like in this area over here is called Cerro de la Estrella, is a stable area, and we have over here Sierra de Santa Catarina, which is also a stable area. The Olivos accident occurred over here, and over here in the locations, in the stars that we label as D1, D2, D3, we have a reports of damage that occurred during the 2017 Puebla earthquake. So what we find when we inspect the intermediate wavelength component is that differential subsidence matches pretty well the location of faults and cracks that are mapped by the city that occur all the time, but it also matches the location of these columns that suffered damage during the 2017 Puebla earthquake that affected Mexico City. If we take this profile that goes from Calle 11 to Zapotitlan station. This is the geological section, and you can see that in the underground we have a lot of volcanic rocks with variable thickness, and we also have the sediment deposits that vary between sands and silts in this kind of layers that appear and disappear everywhere. And if we take we generate a subsidence velocity profile along this section, we see that pretty much the long wavelength subsidence matches the shape of the underground. Of the underground basement. But these little variations of the subsidence signal respond more to variations in the composition of the underground sediments. What is interesting is that we analyze the intermediate wavelength component. We see that the location of the Olivos accident matches this kind of very high indication of differential subsidence that you can actually see from the original velocity profile. So we once again observe that differential subsidence is identified in the location where the accident occurred, even though the city doesn't measure periodically the deformation in those areas. And the same occurs for the D1, D2, D3 locations that experienced damage during the 2017 earthquake. So we suspect that the earthquake exacerbated conditions or damage that pre-existed the earthquake due to differential subsidence. All right, so differential subsidence along the metro system produces damage and service interruptions, and subsidence gradient, which is this tool we developed, can be used as a proxy to determine service life of the infrastructure, and also local signals from our bandpass filtering analysis reveals apparent uplift in elevated lines. We detect hazardous areas, which is potentially useful to plan maintenance of the metro system. We tried to get this information to the metro system at some point, but it was hard to get in touch with them. But still, we consider this a very useful tool. Thank you for your attention. And just as a last slide or couple of slides is a little commercial for our poster presentation in AU if you plan to attend, where we show our results on the mapping of Mexico City, of the whole country, of the whole Mexico, using INSAR from 2014 to 2020, and we show some very interesting examples of displacements. Thank you.
Thank you so much, Dario. That was fascinating and very sobering talk. So yeah, feel free to post any questions in either the Q&A or the chat. Fabien, I'm going to go over the first couple of short questions that we got early on, just real quick, and then I'll pass off to him. Ru Wang was asking sort of about how, in a sense, how different do you think this would be if you looked at the 3D velocities versus the line of sight?
Yeah, thank you. Yeah, so in other studies, recent studies on Mexico City subsidence, where they compare the ascending and descending orbits of Sentinel data, and they obtain 3D velocities, or at least the north-south and east-west component of the signal, as well as the up component. They find that the horizontal component is not very high, and that's from a paper of Francesca Signa, and also from a paper of Batu Osmanoglu, and also still has an analysis on that on the Mexico City subsidence is pretty much vertical. Yeah, the vertical component is so high that the horizontal doesn't really make a very big difference. So I suspect the results wouldn't vary as much, but it would be interesting to to
Okay.
have those.
Yeah, Fabien, if you want to take over, I think.
Yeah.
Yeah, they're all in the
Yes.
chat, so.
Yeah, so yeah, we have a question from Saviyed Mohammed. As you know, the sensitivity of each wavelength is different to see the displacement. So how did you compare the result of different sensors together?
So we're lucky that subsidence in Mexico City is just really huge. So the signal to noise ratio is just really good. And when you compare different wavelengths or results from different from SAR datasets with different wavelengths, it really doesn't make a really big difference unless you're really using a very different consideration for the atmosphere. But no, the subsidence is just really really high. Estelle's paper shows subsidence rates up to 500 millimeters per year, so it's a lot.
Okay, good. Yeah, we have another question, interesting question by Estelle Chaussard. Dario, I imagine that you are using the same reference point for all your data sets. Can you talk about where the reference point is located and how the horizontal vertical motion of the reference point may influence your result? Thank you.
Right. Yeah, you're right, Estelle, it's the same reference point, and for this work, we use the same reference point as Batu, located in the northern part of the city, and also like most of the works use this reference point in the northeast, right? Like where the hills zone start is the same one you use in your work. So yeah, so we use the same, and how the horizontal and vertical motion. Yeah. So the second part, I didn't catch it. Can you talk about how the reference point is located and how the horizontal vertical motion of the reference point may influence your results? Oh yeah, okay. So we assume that the reference point is pretty much stable because it's compared to a GPS located over there, and it's pretty much stable. So yeah, we don't expect a lot of vertical and horizontal in the reference point.
And Dario, to follow up on this question, I was wondering, is there like any GPS station that you can compare or take as a reference? Like, do we have some ground instrumentation measurement that you can compare?
Yes. Yeah, I don't remember the name of the station. Is it GAMC? I don't remember, but yeah, there is a GPS station where the reference point is located, and that was a Batu Osmanoglu in his paper from 2011 started using that reference point, and then a bunch of works who have used that one as well. Mm-hmm. He has a study on. He studies the. He compares systematically the GPS time series to the INSAR time series, and it looks okay. It looks pretty stable.
Great. Okay, so we have another question from Will Prescott. How deep are the peelings typically? Does this imply that the compaction is in very shallow layers?
The depth of the piling depends on the location of the hard layer, but in average, it's estimated to be at 30 meters depth. And the compaction is very shallow. Yeah, it occurs mainly in the uppermost clayey layer, and you can see that in Estelle's paper, Estelle Chaussard's paper that I mentioned. She studies that in depth. Mm-hmm.
Yeah, I think, there is another question from Estelle. I think it's related to what you said at the end on the conclusion. It's like, did Mexico City officials acknowledge previously the role of the differential land subsidence in the Olivos accident?
Yeah, during some interviews, they mentioned that there is differential subsidence, but then in the official reports, as far as I know, no, they don't mention it as a contributing factor. I suppose mainly because they really don't quantify it in doing ground surveys and stuff.
So yeah, the question is like, how do you think like the next step will be to kind of use this INSAR product that you can provide to the officials and try to make the step forward to use this data set?
It's a very tricky question, because I would say, oh yeah, we need to go there and show them the results, and then they will love them and use them. but we did go there and we showed them the results, and they said like, okay, yeah, we'll send you an email. And yeah, and we tried that like at least 3 or 4 times. So actually we haven't been able really to connect to them really well in that sense. But yeah, I suppose keep pushing just to make these results more relevant to them,
Yeah,
and
now
also to
that you are-
translate them to I'm sorry, yeah, to translate
Yeah.
them to geotechnical parameters that they understand, and not just the absolute velocity.
Okay, so we have another question from Ru Wang. In the Olives accident, the location of the accident fits well with a peak in medium wavelength signal. Then there are many peaks in the other places. Does it mean an alert maybe? Or how you can link all the...
Yeah, right. It's that's why we find these results interesting, because we consider that all these areas experience differential subsidence, but then you need to think also of the frequency with which they repair or they perform maintenance. So if you have a small differential subsidence but you never perform maintenance at that point, it's probably more likely that something occurs over there than in another area with huge differential subsidence, but where they perform maintenance very frequently. But yeah, exactly, this differential subsidence is could possibly indicate areas of that require attention.
And Dario, in terms of reparation, like do they base only on the report and the survey of cracks, and they are repairing where the location where there is more like damage, or do they use other like measurement or other like criteria to do the reparation in the metro line?
It depends. I mean, I'm not really kind of in touch with them to know like a lot of details on that, but as far as I understand, they use a little cart that they they travel with this little cart through the system, and they detect the differential movements of the or the areas of the railway where there is a bending. But for the piles, I guess they perform inspections visually, and civil engineers usually place instruments. There is a paper where they placed instruments like a few columns away from where the accident happened, but we don't have measurements from the civil engineering surveys where the accident happened. So yeah, the instrumentation is not like everywhere, and I suppose they go from time to time and they perform repairs where they consider it's necessary, but I'm not really sure how systematic that is.
Okay, thank you. So we have another question from John Galetka. There was a petrol pipeline tragedy several years ago somewhere in the Valley of Mexico. Do you know if this happened in one of these zones of high differential subsidence?
I have no idea. No, I haven't looked into that, but I would bet so. No, I'm not sure. I would need to locate it on the map. But if you share with me your email, maybe I can send you a screenshot of how this looks. That's an interesting question. Mm-hmm.
Great. So I think we are done with all the questions for today's webinar. I don't know if Tamara or Chris, you want to close the webinar?
Yeah, thank you so much, Fabien, for doing the questions. Yeah, thank you so much, Dario, for very fascinating and interesting talk, and a lot to think about as far as city planning. I guess I have one question that came to mind. Do you know, is there any way to, are there any sort of engineering inventions that something like building flexibility into like attachment points on how on the structure of the metro or something like that, that would maybe allow for a little bit of differential motion without causing like a catastrophic amount of bending, or is that also risky because of like earthquake shaking?
Well, in general, the columns can stand a little bit of deformation, but then you say, for example, these kind of bridges can stand, I don't know, 5 centimeters of differential deformation, but that needs to happen in a 50-year period. So you kind of, when you build the system, you can of take that into account, because if you surpass that 5 centimeters, maybe there's going to be first a problem like visually because it doesn't look good, and then a problem with the stability. But also in the case of the railways, they have kind of layers of different kinds of materials to kind of level and compensate for the deformation that they have, especially in the lines where they have a huge differential deformation like all over the year. And thank you so much for having me and for the space.
Yeah, if anybody has additional questions or interests, and I'm sure there will be many, feel free to contact Dario by any means. And yeah, please do check out his AGU presentation. I'll be there. I look forward to it, Dario. Thank you so much for a great talk, and look forward to hearing more from you in the future.
Thank you so much, guys.